All right. Okay. I think I'm sure more people will trickle in as the minutes go by, but I figure we go ahead and get started if there aren't any objections. So the plan for this morning block of the hack week, we're going to kind of pick up where we were yesterday. So we're going to go back to working on the formulary. So we'll go back to kind of pick up where we left off and kind of add to whatever formulary functionality you were working on, and kind of build up the formulary package for the hack week, so all of you can get experience with the process. But before going out to breakout groups, I thought it'd be useful to go through Plasma.Pi's documentation, so you're all a little more familiar with the documentation and how to read it, and that will give you an insight of what currently exists in the formulary as well. I might show some side-to-side comparison with code at the same time. And then I have a notebook in the resources directory that highlights some of the more sophisticated functionality that's used within the formulary. So I wanted to demonstrate that so you can use it on your own formulary functions. All right, are there any questions before I get going? All righty. Let me get my share going. All right. Can everyone see my web browser?
Yep, that's good.
Okay, so I'm going to start off with Plasma.Pi's documentation. So the documentation site is docs.plasmapi.org. And that'll take you directly to the documentation site. Okay. As I mentioned earlier in the hack week, this bottom tab that you see here, if you click that, they'll pull up with several different versions of the documentation. Stable is the one that corresponds to the latest release. So if you've installed Plasma.Pi through Anaconda or through pip, this is likely where you're going to want to be. If you're working with the code that's currently on Plasma.Pi's main branch, that's what corresponds to latest. So this would be the code that's directly on the main branch in GitHub. And then if you're working with an old version, you can go directly to the old version's code as well. Okay, so I'm going to stick in stable for now. So the way that we have this set up, so is the font size in here okay for everyone, or is it too big or too small?
It's good to me.
Okay. Just feel free to leave a comment in the chat if you want me to change anything. All right, so the Plasma.Pi documentation, we break it up into these groups. So in the first steps are just installing Plasma.Pi, which we've gone over earlier in this week. There's also there's information on how to do it through pip, Anaconda, Conda, Navigator directly from GitHub. Getting started, these are just some Jupyter notebooks that discuss some very fundamental functionality associated with using the package. You basically run across this functionality with anything that you use in the package. Examples, so this is a place where we have all of the notebooks associated with Plasma.Pi. And our goal at Plasma.Pi when writing documentation is not for the documentation must be informative, but our whole goal is also for it to be educational. So if a notebook is written on like a dispersion relationship, it's going to try and discuss the origins of that dispersion relationship, the regimes that it works in, the regimes that it doesn't work in, try and give a little background of where it came from and what it's doing. Additionally, first steps, instructions on how to give feedback and communicate with us, instructions on how to contribute to Plasma Pi, code of conduct, which I believe is the same as the code of conduct we use for the hack week, and how to acknowledge and cite the package if you end up using it for a publication. Okay, so that's kind of the first block. The second block, this is the one that directly maps to the Plasma Pi package itself. So if we go to GitHub, Plasma Pi, so we're going to GitHub's Plasma Pi package repo. Okay, so this root directory, you can think the root directory as kind of the package management level, and the code actually sits in the Plasma Pi subdirectory. Okay, so you'll see here, these are all the sub packages. So you got your analysis and diagnostics. So if we jump back to documentation, you got your analysis and diagnostics. You got your dispersion sub package, and you got your dispersion sub package. And then similarly, formulary, particles, simulation, a plasma calculator. That kind of not follows the scheme. The plasma calculator isn't on the main level. There's a plasma calculator that's in the works that actually sits here in the utilities subdirectory. And it's basically when you install Plasma Pi, you can launch it from the command line, and it pops up with a little web GUI where you can put in values and just calculate simple plasma parameters. But it is in its early forms of development at the moment. Okay, plasma objects, and then package utilities as well. So package utilities is basically not so much plasma functionality, but helpful tools that we use to write the Plasma Pi package. Okay, you go down further, you get your contributor guide. So this will have additional details if you decide to contribute to Plasma Pi. Our code development guidelines, how to create change logs, how to write documentation, how to write testing. You don't have to worry about the release guide. That's more for us, the maintainers. And then all the rest. So this has things like authors and credits, bibliography. The change log is a log of all the things. So these are all the people that contributed to the last release. And if you keep scrolling down, you have basically a log of all the stuff that was changed between the release of 07 and the release of 08.1. So if you're trying to backtrack when something was added, this is another place you can go to kind of search, and it will, so for the spectral density changelog entry, it links back to the pull request that actually created it. So if you click on that, you can go back to the pull request that's associated with this new functionality. You can read through the discussion. You can look at the files that were actually changed. So that's a way that you can kind of trace back stuff. Another way to interact with this, if you come up here right underneath the search bar, you can search if you're looking for something specific, but you can also go to the modules. If you go to the modules, it will have a breakdown of the entire package. So let's say you really wanted alphane speed. So if you come in here, it's in the formulary and it's in the speeds package, and that will take you directly to the module that has alphane speed in it. So again, you would go to modules, you come down to the formulary section, speeds, you click on that, it takes you to the module documentation, and then you can go to the specific functionality within that. Now, this documentation is actually auto-generated directly from your code. So let's go back to the package, close this up. So we go back to the package, okay, and we go to the formulary, and we go to the speeds module, okay, and we scroll down and we find alphane speed, okay. Okay, this is a little small. All right. Right after the signature line for the alphane speed, we have here, which is called the doc string. This is the stuff that gets automatically generated into the documentation. So everything that you see here, calculate the alphane speed and the alphane speed, VA is typical propagation of the magnetic disturbances in a plasma as given by function, is this calculated the alphane speed. The alphane speed VA is the typical propagation speed. So that's how we write most of our document. So we have an auto docker, so it will recognize all these doc strings and will automatically put it into the documentation to document how the functionality works, to document the background of the functionality and so forth. Same thing happens with the speed module itself. If you come up to the top here, there's a doc string on the module level, functions to calculate a fundamental plasma speed parameters. So if we come back here, and let's navigate a little differently. So we go back to the landing page. If we come down to formulary, okay, you can, in this top chart here, you can go directly to speeds, and this will take you to the module documentation. Functions to calculate the fundamental plasma speed parameters. Okay. So then if you look at the documentation, it always starts with a little brief summary. This is known as the signature line up here. So this lists all of the required or optional input arguments and the types that are expected. For example, you have an input argument of B and you're expecting units of Tesla. You have an input argument of density and it's expecting to be a number density per meter cubed or kilograms per meter cubed. Okay. But you can also scroll down and get additional information. So for example, for densities, it's either the ion number density Ni in units convertible to meters inverse cubed, or the total mass density in kilograms per meters cubed. Okay, so they don't have to be exactly these units. They just have to be convertible to these units. Okay, and now this function also has an alias, VA, which is also listed here. Keep scrolling down, it gives you what the return and rate and what the return type is, what it's returning back, and several cases where exceptions might be raised in warnings.
Oh, hey, Eric, I have a question.
Yeah.
What's the underscore at the end of your alias there?
This here.
Mm-hmm.
So
For those unfamiliar with that.
Well, okay. I think in Plasma Pi, we take an approach of explicit is best. Hence why you have this long name alphane speed, because then when you see, you immediately know what it is. But we also recognize that when people are going to use this, they're likely going to import it as VA. Because if you're writing alphane speed over and over and over again, or plasma frequency, which is even a longer name, you get long lines of code and it gets really messy really quick. And we recognize in the plasma community that there are a lot of these parameters have recognizable symbols. For example, alphane speed, you have VA. Plasma frequency, you have WP. Cyclotron frequency, you have WC or OC. So they're commonly recognized shorthands. So we want to provide the same thing. So that's why I say for alphane speed, you have VA. However, we want to avoid a situation in which maybe you have already used VA in your code and you import our VA. If you're not paying attention and we've just named ours VA, then we would overwrite your VA that you already had in your code. So we wanted to avoid the situation where we might actually be overwriting stuff you've already defined in your own code, in your own notebook, in a previous cell or something like that. So our method is to add a single underscore after it. So this is to prevent namespace collision with your own workspace. And that's the convention we use for all of our aliases. So all of our aliases will have a trailing underscore on it.
Okay, thanks.
Yep. Are there any questions on that? That was probably longer winded than Steve was actually expecting.
No, that was great.
Not only was it great, I'm really appreciative that Steve asked the question, because culture, literally what you decide to set up as conventions, are extremely important. And this one was clever. I was thinking to myself, gee, I wonder how they're avoiding namespace collision. And there it was.
Mm-hmm. Thank you, Vincent and Steve. Now, we don't give aliases to all functionality. Our rule of thumb is the functionality must have a recognizable convention in the community already. Because if it's not, then people aren't going to recognize it when they immediately read their code. So it has to already have a convention that exists. So in the documentation, if you keep scrolling down, we typically have a notes and examples section. So our practice is at the very beginning, we tried to keep this description as concise as possible, but in doing that, you often miss details. And so when that's the case, we expand on the original description down here in the notes section. And so this is where it gives a little more of the theory of where the functionality came from. There might be more references. There might be a little derivation or something like that. It's just an expansion of what you see at the very top. And then typically we have some kind of an example that shows how to use the function. Okay. Back on aliases. So let's go back to the formulary. So back to the formulary. So we provide this little table right off the bat so you can navigate to the individual modules. But if you look in this left-hand panel, you have an example section. So if you look in an example section, this would be all the notebooks that are associated with the formulary functionality. So you can go in here and see how the functionality is being used for specific real-world examples. And we're always trying to expand this. And even further down, you get to an API section here. So this is going to list out all, so we're currently sitting in the formulary documentation. So it's going to list out all the formulary subpackages and modules, excuse me, all the classes and functions also within the formulary. So you can keep scrolling down. So here's all the sub modules. So here's the speed one. And Nick found this kind of new little thing that we've introduced that I've kind of been ignoring as we go along. But if you hover over a functionality, it'll pop up with a little quick dialogue of the linked functionality. So you can kind of preview it before you go to it, which I find fairly handy. Keep scrolling down, you get your classes. This is a little inheritance diagram. So in this case, say a circular wire inherits from the wire class, which inherits from the magnetostatics class. These are all the functions in here. So we do expose, so as you saw, this alpha and speed was was written in the speeds module, but we do expose it on the top formulary level as well. So you don't have to do from plasmapi.formula.speeds import alphane speed. You can just do from plasmapi.formulary import alphane speed, which is also the way that we recommend that you do it. But if you keep scrolling down, we also have a section for aliases. It kind of describes what aliases are, and then it will show you all the aliases that also exist. Okay. And then we have another little thing that we've been slowly introducing that we call light functions. They don't cover all formulary. These ones I don't use at the moment. The one thing that's great about units is we can basically guarantee that we can give you the correct calculation regardless of what units you give us, because then we can properly manage it and get you, so we can properly handle the fact that you're giving centimeters instead of meters, or light years instead of seconds. Like, we can handle those situations, so you're always doing the appropriate calculation. It's handling the units. But the problem with doing that, it's great for robustness, but it comes at the penalty of speed. And so if you get to the point where you're doing some kind of repetitive calculation, some kind of numerical calculation, you need to start favoring speed over the robustness. Especially since once you inside the routine that you're writing, you can pretty much guarantee you've already done all the work to make sure you have the right units. So these light functions are meant for that scenario when you're doing some kind of numerical calculation where speed matters, because in these functions, we basically stripped away all the protections. So now you're at risk. It's no longer going to tell you that you've done something wrong. It's assuming that you've done all your work and you're doing it right. So for now, don't touch light functions. Just stick with the normal ones. Yes, another product of procrastination-driven development. All right. Any questions on the documentation site? So I will add, for all those that were contributing to the Hack Week repo, you'll often notice when you were opening up your pull request, you had this one little check running, this docs check that would run every time you added, when you open up your pull request and every time you added a new commit to your pull request. What this is doing is actually generating the documentation site for the Hack Week package. So you can go to the documentation for the Hack Week package. So if you're in your pull request and you click on details, it will open up the documentation for that pull request. So if you look down the bottom here, you can see a 60, or right underneath the Hack Week, you see a 60. And that's because it's being associated with this pull request 60. So that's the one associated with your pull request. If you want to go to the overall package documentation, you do docs.hack.plasmapi.org. So if you go to that website, docs.hack.plasmapi, it will open up the documentation that is linked to the main branch of the Hack Week. So as we continue filling it out, all your work will be adding into this. Now, I'm not sure any of the current pull requests had doc strings added to them. Oh, this one did. So if we go back, nope. Okay, so we also have to do a manual step to get it in there. So that's why you're not seeing the documentation here yet. But we'll likely get into that step probably by the end of today, as we iterate through your functionality. That's another layer of functionality added on your initial layer. So we're kind of trying to build ourselves up slowly. All right, any questions? Okie dokie. I'm now gonna, I have a notebook available that will demo some additional functionality that's going to be useful in constructing your own formulary functions. So if we go back to the Hack Week repository, so GitHub / PlasmaPi / Hack Week. Okay, so we're in our Hack Week repository. And you go to resources and you scroll all the way down. Okay, and you click this blank notebook here. Sorry, not this first notebook, but the binder notebook, and that will launch the binder session associated with the notebook that I will go through. So I'm actually going to create a poll real quick. So once you have your notebook up and running, please fill out the poll, and once most people are there, then I'll start the demo. And that's not what I wanted to do. Okay. Okay. Okay, I'm launching the poll now. So once you get it open, it should look like this with a whole bunch of blank cells, very similar to the notebook demo that Nick did on Monday. All right, so for the notebook, you want to go back to the resources directory in the PlasmaPi repo. Okay. Scroll all the way down to the README, bottom 2 lines of the README, and click the launch binder associated with the blank notebook. Not a problem. Thank you, Nick. Nick put a link into the chat. All righty. If you're still waiting for the notebook to get going, can you please leave a comment in the chat? Otherwise, I think we got most people up and running, and I will get going.
Or you can raise your hand in the
Or you
Okay.
right? Yeah. Thank you, Nick. All righty. Well, thank you. I'll get started then. So one of the things that I have mentioned throughout the hack week, whoops, that's not what I want to do. The Plasma Pi, the functionality contained in the Plasma Pi formulary is unit agnostic. So it doesn't care what units you give it as long as it's convertible to the expected type. So obviously it's gonna complain if you give it seconds when you're expecting meters. But if it's inspecting seconds and you give it, or if it's expecting meters and you give it light years, then it's still going to be fine. Okay. So to kind of showcase this, so I have the first cell where you're just going to import AstroPi units. So import AstroPi units as U, which is the general convention. And I'm going to import the Debye length. So one of the things that's nice about Jupyter Lab, I think this will still have work in Binder. So if you do Debye length and you start typing it out and you hit tab, it should autocomplete. You do your close parentheses and you hold down Shift Tab. It will pop up with a dialog box that shows that shows the documentation for said function. So you can look at this and it's telling you that the first argument is the temperature, the electron temperature, and it's expecting Kelvin. And the second unit is the electron number density in units of inverse meters cubed. And it's going to return a length in meters. And you can keep scrolling down here and it'll give you additional information about each of these parameters as well. So everything you see here is the same as the doc string that I showed for the alphane speed. So it pulls, this documentation is a doc string for this function. So it pulls that and renders it here. Okay, so let's define an electron temperature. So TE equals 115,000 Kelvin. So 115,000 times U dot K. So this is about 10 EV, roughly, okay? And let's pick a density of N E equals to 2E to the 18 times U dot meters inverse cubed, okay? Now, if you look at this, TE and NE are both positional or keyword arguments. So you can enter this in as TE, NE, or you can enter this in as TE equals NE, TE, and NE equals NE. Okay. Hit Shift Enter, and it will spit out the Debye length in meters. Okay.
For those who are still struggling with some syntax, are there supposed to be spaces around the input assignment operators, or are there specifically supposed to be no spaces?
The Pepe convention here is not to have spaces.
Thank you.
Yep.
It should work with or without spaces.
In the end, Python doesn't care if you have spaces or not, but the PEP8 convention is to not have spaces. All right, so let's do the same calculation, but let's do it in a different set of units. So let's define a new variable TE, And let's actually put this TE in EV, so in electron volts. Okay, so we got TE in EV is equal to TE, so our previous electron temperature, and we'll do dot 2. So now we're using AstroPi units to convert our Kelvin temperature into electron volts. So we got dot 2 U dot EV. So we want to go to electron volts. Now, this is a unconventional unit conversion. So if you do shift enter here, you'll get an error. It doesn't know how to handle, AstroPi by default does not know how to handle this unit conversion. So, but they have a solution for this. They have a thing called equivalency. So if we do go back and we do comma equivalencies equals U dot temperature, you hit tab, so you can do normal temperature or you can do temperature energy. You want temperature energy and close the brackets. So this is basically a function that returns, well, the old way, it was a function that returned a list of functions that tells the converter what to use to actually do the conversion. So it's just additional library on how to do the conversion. So now if we do this and we do shift enter, and let's do T, so we can see the output. We do TE in EV, hit tab again so you can easily autocomplete, and then shift enter, and you see we're near 10 EV. Okay. So let's do the same thing for the electron density. So let's do NE underscore in, let's do it in light seconds cubed equals, we're going to do the same thing as we did with TE. So we do NE dot 2 close, and now we want to convert this to light seconds inverse cubed. Okay, now this is a standard conversion, so we don't need any equivalencies. So we can see the output. I'm just going to do this, put into a 2-element tuple. So you put parentheses at the beginning, put a comma after TE and NV, and now we do NE, hit tab. We can do NE in light seconds cubed, close the parentheses. Okay, shift enter. And so now we see TE is about 10 EV, and the electron density is about 5.3 times 10 to the 43 per light seconds cubed. Okay. So now we will put this back into the debye length. So we start typing debye length. We can go hit tab and it will autocomplete. Okay. The first argument is temperature. So we do TE, hit tab again. And we want TE in EV. And we'll do the same thing for the density. NE, hit tab, and we'll select NE in light seconds cubed. Shift enter to execute, and you'll see we'll get the same value as we did with SI units. Is the binder notebook not working correctly? It is now. Okay, cool.
Eric, I have a question.
Yeah.
So you get devalent meter, but what if I don't want a devalent meter? What if I want it in, I don't know, inches? Can I tell it in the same step?
Yes, you can. So if you do it like this, the best way to think about this is, now that you have the function here, think of this now as your variable. So think of this at okay, so I'll do it two ways. So if I do val equals that, so I'm going to get the value back. Okay, whoops. I can do val dot two. So now I want to convert it to, you said you want it in inches, right?
Right, yeah.
So you do u dot imperial dot inches, inch. Okay. Shift enter, and you get it in inches. Now you can do this all in one step. So if we get rid of value or val, and we put it all in one line, dot two, close parentheses, u dot imperial dot inch. Okay. That will do it all in one line as well.
Okay.
And so you, yeah.
Yeah, I was just wondering if there was a way to put it in a keyword kind of thing, like, inside the function itself to do that. I guess not.
No, not inside the function.
Okay. Cool, thanks.
The only thing that we have that's similar to that is for the frequencies. There is a keyword in frequencies that says 2 hertz. So by default, all of our frequency functions return units in radians per second. If you use the 2 hertz keywords, you can get it back in hertz with the factor of 2 pi correction, or adjustment, I should say. But yeah, the rule of thumb for Plasma Pi functionality is everything is SI. So you don't have to give it SI, but it will always return SI. All right, so how is this done? We've developed this function called the validate quantities. This is our unit enforcer. So if you remember back to yesterday, you probably saw that a lot of our functionality had these couple additional lines right before them. Those, you'll see what that is down the line, but those are what's enforcing the values and units of stuff that you're putting into the function. So to get started, okay, before getting validates quantity, so let's define a kinetic, let's calculate the kinetic energy. So we're going to define a kinetic energy, I'm going to call this light, okay? And it's going to take arguments of mass and velocity, okay? Simple enough calculations. We go return 0.5 times mass times velocity squared. Okay. So we'll go kinetic energy light. You can hit tab to autocomplete. And let's use a mass equal to 1233 for no particular reason, and a velocity equal to 39.34, again for no particular reason. Okay, hit shift enter, and I did a minus sign instead of an equal sign. Okay, shift enter, and we get a value, but we have no protections. We don't know what were the units of these? What were the units of these? What are the units of the output? We have no confidence on what's going on. And so now we can start introducing units. So we'll do from Plasma Pi, tab to complete, dot utils, dot decorators, okay, import validate quantities, and shift enter. So validate quantities itself is just the function. Okay. And so what we'll end up doing is let's and this validate quantities is what's going to do the unit enforcement. So let's define, say, validate quantities as a function given a set of parameters, and it will validate the inputs and outputs of another function, but it also returns a function. I know I said a lot there. So let me show it, and then we can talk about it in a little more detail. So we're going to say kinetic energy is equal to validate quantities. We can close the tabs, and if we hit Shift Tab as before, it shows you what the arguments are for validate quantities. So it has an input argument of func. So this is the function that you basically want to enforce units on. It has this validations on return. So you use this keyword to control what the return argument should look like. Okay. And then you have the star validation. So this is a little bit of a magic. Basically, what will happen is any keyword you use will be grouped into the star validations. So in this case, what we're going to do is we're going to go func equals kinetic energy light. Okay. And then the two input arguments we want to enforce are mass and velocity. And we know we want our mass to equal u dot kilograms. So we want that to be in kilograms. And we want our velocity to equal u dot meters per second. Okay. So what's happening in this case is this mass and velocity keyword are essentially being grouped in this validations. So it allows you to, in this case, it allows you to, the keywords you use here are identical to the names of the arguments for the function you're operating on. Okay. And this whole process returns back a function. So it doesn't change any of the internal behaviors of your original function. It just returns back another function, but now it has unit enforcement on mass and velocity. So if I go ahead, I'm going to come up here and I'm going to copy and paste my original line for kinetic energy. So kinetic energy, make sure if you're doing it that way to delete the light part. So now we want to use this function of kinetic energy. So you have kinetic energy, mass equals 1233 and velocity equals 39.24. Shift enter, and okay, this is different. We're now getting two warnings, but if we read the warnings, it's saying that there's no, the argument mass has no specified units, but it was expecting units of kilograms. But because you didn't specify anything, it's just going to assume kilograms and apply it. So we don't want to stop the calculation. So we give you a warning that we're doing something that might not have been expected. So when you guys write new functions for the PlasmaPy library, do you write a raw version of the function and then use this? Yes, with an asterisk to it. You'll see how it works a little better when I get further down into the demo. Okay. Another weird thing is now we have this kind of mashup of units on the return value that well, we know what it is, but it's not clean either. So let's get rid of this warning first. So the easiest way to get rid of the warning. So let's go back up and copy the kinetic energy expression. Okay. And instead of just doing 1233, we'll add in a u times kilograms. And for velocity, we'll add in a u per u dot meters over u dot seconds. So now if I do shift enter, I put in 2 times. So let's do shift enter again. All right. Now we don't have any more warnings because we're giving the units that are expected. But we still have this kind of garbled mess for a return unit. Okay. So let's go back up here and copy the original enforcement we did earlier. So we'll copy this line up here and we'll paste it back. So as I alluded to, if we go back and do a shift tab to get the documentation, we have this keyword called validations on return. So we can go ahead and we can go validations on return, and we can tell this we want it to be u dot joules. Okay. I believe that will be right. Yeah, I think u dot j will be right. So now let's go back up here and copy the previous line. Okay. Paste that in. So we're not changing any way we're calling it. So we've actually, because of this line that I'm highlighting now, kinetic energy is now new. It's a completely new function than the one we did before. Okay. So now if I do shift enter, I get an answer that's in joules. All right. Any questions so far?
Can we put any units of energy there in validation on return, and it will give us the right answer in that units, or does it have to be SI?
It should. So if we do EV, we should get an answer in EV.
Oh, cool.
Yep. So even though we enforce SI units in Plasma Pi, if you use this tool, you can enforce a different set of units. So let's put it back to joules. Okay. All right, but we still have something a little weird here. So let's go back and copy the kinetic energy expression that we just did. But if we put in a negative mass, which makes no sense, we get negative energy. So we have another weird problem here. I'm like, where the function is allowing values that shouldn't be allowed. So we have a solution for this using validate quantities. So let's go back up here and copy the expression where we use validations on returns. Okay, and we'll paste that into the next cell. Okay. I'm going to clean this up a little bit.
This is a made-up example, but yeah, for kinetic energy, we could actually have, or for mass, we could actually have a loss of mass due to a fusion event. Mm-hmm. So I still think that might be a useful calculation to do, but I realize that this is for validation.
Yes, this is for validation. I mean, these are those things that you think about when you're writing functionality and the issues that you try to solve. So the people that are using it are readily aware of what's going on. Okay, so this line is getting rather long, so I'm gonna clean it up a little bit. So I'm gonna go enter here. I'm gonna do an enter after each comma. So I'm Nick, remind me, what's the terminology for this? I don't remember. You remember?
For
line continuation?
Yeah. Yeah. Nick?
Yeah, that sounds about right.
Yeah, that sounds about right. All right. So now for mass, we no longer just want to validate units. We want to validate values. So for here, instead of just declaring mass equal to the unit I want it, we can actually have a dictionary here. Okay. So we still want to validate units. So the first key we want is units. And so now that's telling, so we're still validating kilograms as units, but we also want to make sure the value can be negative. Okay, that's false. We don't want it to be negative. So if I'm in here and I do shift tab again, I keep scrolling down on the documentation, you'll see that I run into this table here. This table is a list of all the keys that one of these dictionaries can contain. So we have units. So that's the one that we continue using. You have equivalencies. By default, you don't do this. But let's say, for example, you had temperature and you wanted to convert between temperature and EV. As I illustrated above, we need to specify an equivalency. So that's what you would specify here. Okay. Yeah, we have the none shall pass. So that allows you to pass in none values. You can have, yeah, you have can be negative. I guess you can consider that
It's
Easter
just a
egg.
scratch.
Yeah. So I'll let you all know we do have one Easter egg in the package. There's one Easter egg. It was quite ingenious when one of our contributors came up with it, so we couldn't say no to it. So you can also validate on all these things. So you can validate it on it being the values being complex, if they can be infinite or NaN values, or can be zero values. So in fact, we can probably even in this case, if you wanted to, you can do can be zero false, but I'm not going to do that for this demo. Okay. So now we have added both unit validations and value validation. So this is why this is called validate quantities, because quantities is both a value and a unit. It's not just a unit, it's a value and a unit. So this function allows you to enforce both units and values. Okay, so we go back up to the previous line and copy our expression for kinetic energy, paste that in, and now I'll get an error. And it tells me, if I keep scrolling down, the argument mass to function kinetic energy, I'll get into this later, cannot contain negative numbers. Okay. Any questions? All right. So this is nice, but this implementation is a little messy, to say the least. So we can use Python's sugar syntax for decorators. And that's essentially what validate quantities is doing. A decorator is a function that wraps around another function. So basically, your decorator is doing some calculations, passing those on to the function that you're wrapping, and then can or doesn't do additional operations on the return of said function, and then it gives it back to the user. So in this case, what's happening with the validate quantities is when I'm executing kinetic energy, these mass and velocity arguments are first being passed to validate quantities. It's doing all of its checks on these. And then after it does all those checks, it takes the resulting mass and velocity arguments, whatever validate quantity is done to them, and has passed it back to kinetic energy light. Kinetic energy light does its calculation, returns a value. After it returns a value, validate quantity grabs that return value, does some additional calculations on it to make sure that it has units of joules, and then returns that value to you. Okay. So this allows us to just use this function opposed to rewriting that code for every single function we have. Okay. So Python has what are a sugar syntax, so a pretty syntax for using decorators. So in this case, I'm going to go ahead and I'm going to start by copying these lines up here, just the validate expression. So I'm going to copy those. Actually, no, I'll write it out in detail. So what I'm going to do is I'm going to write in at validate quantities, close my parentheses. Okay. I'm going to press return. I'm going to define my function. So I'm going to define kinetic energy. Okay. And again, it has arguments of mass and velocity. Okay, colon to stop the definition. And we're going to return 0.5 times mass times velocity squared. Okay. In here, I still want to validate the same stuff I was doing before. So I'm going to do mass equals units. So dictionary, so you curly brackets, and then your first key is going to be units, U dot kilograms. And then your second one is going to be can be negative, colon, false. Okay, put a comma. Next line will be for velocity. So we have velocity equals U dot meters divided by U dot seconds, comma, and we're going to do validations on return equals U dot J for joules. Okay, so let's go back up, and we're going to copy this kinetic energy line. Okay, go enter, enter, paste that line. So now this kinetic energy is referring to this one we just defined. Okay, shift enter. Oh, let's get rid of the minus sign so we don't get errors anymore. And shift enter. Okay. All right, so now we've introduced a way where instead of having to declare the function and then insert it into another function to get the unit validated function, we don't have to do all those steps. We can do it all in one here. However, we can make this even cleaner. So I'm going to add another cell. I'm going to come back up here and I'm going to copy my definition of kinetic energy. And I'm going to paste that back down. How can I make this cleaner? Validate quantities knows how to read type annotations. Okay, this is great because now I can use type annotations in my function signature that not only unit validate quantities can pick up, but will also show up in documentation. Okay, so for mass, I'm going to do colon U dot kilograms. For velocity, I'm going to do colon U dot meters divide U dot seconds. And I'm going to put a return annotation. So space minus sign, rightward arrow equals U dot J. By doing that, I can now delete the velocity and validations on return line. And I can delete this units for mass because now that's defined here in the annotations, and I can bring this all back to one line. Do you take a big performance hit for doing validations? Yes, you can. Yes, you can. And that's why I mentioned earlier, we're slowly introducing the light functions. So if you're doing some kind of numerical calculation where you're performing the same calculation over and over, and you know you have the right units going into it, you can use that. You just no longer have the safeguards of validations. But yes, you do have a performance hit with it. Now, your performance hit isn't universally the same for all conditions. If your units are the expected units, your time penalty is not as bad as if your units are not the correct units, because the checks on just checking you have your right units are a lot quicker than doing the check and doing the conversion. Okay. All right. So now let's go back up and copy the previous kinetic energy. We said earlier that these in argument declarations of units aren't requirements, but suggestions. Does this syntax provide weaker unit enforcement? No. So annotations aren't necessary in Python. They're just that, annotations. They don't, by default in Python, they don't enforce any types of values going into your function, because Python is not a typed programming language. However, what we're doing is we're leveraging annotations to do our own enforcement. So that statement you heard previously was said basically on a Python semantics kind of thing, a point of view, I should say. Now it's not 100% true, because we're adding additional functionality that uses annotation to do enforcement. And next question, could we have a quick primer on decorators? I don't see how the kinetic energy function knows about the decorator. The kinetic energy function does not know about the decorator. The functionality does not know about it. What essentially happening, I can go into decorators with you in more detail later. It's a little beyond the current scope now, but think about it this way. This decorator, this kinetic energy function here does not know about the decorator, but the decorator knows about the kinetic energy function. And so when Python does its compiling, the function you actually get is a version of validate quantities who is masquerading as kinetic energy. So okay. Okay, so I'm going to go back up here. I'm going to copy this line, paste it back in, and we'll see that everything works as before. Okay, so now let me prove to you that this works on non-standard units. So let's pick a mass equal to 2718 times u dot imperial dot lb, which just happens to be the mass of a DeLorean. And we'll pick a velocity equal to 88 times u dot.
Did you want the imperial dot? Yeah.
Thank you. Dot mile divided by u dot hour, and we'll do kinetic energy. Mass equals mass, and velocity, tab for completion, equals velocity. Shift enter. All right, so we get basically the same energy. Completely not intended. Any questions? All right, so
That's an astonishing coincidence.
astonishing, I know. It's like someone has some forethought. All right, this is great, but
I have a question about decorator.
yeah.
So in decorator, you put in the SI units. Does it have to be SI unit, or could it be any velocity units as long as it is consistent?
Any velocity units you want.
Okay.
Yeah. Okay, so
And it has to be a time for a break.
you just got me, Nick. Yes, I was going to say we're 10 minutes after. This is a good stopping point. So let's stop now, and then I can come on to the last bit afterwards. So we'll come back at 25 after the hour. Excellent.
Can we use this break to go over about the question that Clement asked about the
Sure.
decorator? I'm very
Sure.
confused how the function knows. Even though I have used the exact same thing for my coding, I still don't know how the function knows which decorator to use.
How the function know? Like I said, the function doesn't know.
So
Okay,
how
so
do you? Yeah.
okay, let's see if I can find a reasonable. I'm not going to use validate quantities as the example decorator because it is a complicated one. So let me go decorators. Let me try helpers, modify docstring, reserve signature. I think this might be a decent one to use. Is that a decent one to use? Okay, this is a. All right,
Eric, were you
so
intending to share your screen?
yeah, I'm just pulling up. I'm trying to pull up an example before I shared. All right, so okay, this is probably the simplest decorator you can do. So I'm going to show this one first. So we have a decorator called preserve signature. And it takes in a function. And so this decorator is not actually touching any arguments whatsoever. It's not touching input arguments. It's not touching output arguments. What it's doing is it's inspecting the function you passed in to see if it has a signature dunder. If not, it inspects the function f. So in our case, f would be kinetic energy. It inspects that function to get that signature and then adds the signature dunder back onto f and returns f. So this is the simplest type of decorator you can have because it's actually not touching any of the arguments whatsoever. Questions?
I understood some of that. Yes.
Say that again.
I understood some of that.
Understood some of that. How about maybe I can do a live example. Let's see if I can do this. All right. From func tools import wraps. So let's go. See if I can remember how to do this. Define mult 10. So this one would have, trying to remember the pattern, colon, define wraps, define wrapper, star args, sar, keyword args. We want to home.
Hey, Eric.
Yeah.
One of the things that I think makes it easier to understand how decorators work is to first understand that you can pass functions as arguments. If you live in a world where you've never actually used a function as an argument or a pointer to a function, which I've existed prior to that capability, it's hard to see, but the reality is if you can pass that function, then you can call that function inside of another function. And it can be passed in this anonymous sort of way. So,
well, maybe to expand on that even more is everything in Python is an object. Everything in Python is an object. And therefore, anything could be passed as an argument. It could be a variable. It could be an instance of a class. It could be a class itself. It could be a method to a class. It could be a function, as we're doing here. So basically, you can pass anything in Python as an argument or a return value.
Yeah, in this case, what ends up happening is you pass it as a function, and you execute the function's capability, and then you add to that function with whatever is appending or modifying some of the arguments before they go into the function.
Mm-hmm.
So the heart of it is the fact that you're calling that function within a function.
Say that last part again.
That you're calling a function within a function.
Yes. So that's what I'm kind of writing out here is I'm calling a function within a function. So what I was hoping to do is get down the basic pattern for a wrapper and then describe what's going on, because I think having the example put down will help explain how it works.
Yeah, I figured I would be talking while you were coding.
Oh, okay. Continue talking, then I'm going to continue coding.
I'm done.
You're done. Arg1.
Yeah, some of the early examples that I saw of decorators, for easy mental paradigms, it looked like injecting code into your function. And that was how it was described in a lot of the documentation that I read early on.
It's not so much injecting code into your function.
I agree.
Though.
I agree. That I thought that paradigm was actually kind of weak.
Yeah.
After I became familiar, because really what it's doing is calling your function within a function.
Yeah. All right. So let's see if I got this all right. Okay. So now if I do, so I've defined, there are flaws with this design, but the idea is I defined a wrapper that would multiply the first argument that I pass. So in this case, the idea is I have a function that I've named foo that takes one argument. What this wrapper will do, what this decorator will do, is it will take that first argument and multiply it by 10 before passing it to foo. So if I do foo1, the output should be 10 and not a error. There's no attribute module. I might have to do. Do I have to do that?
Are you missing? Okay.
No. Why am I? Let's just chat. Okay, give me a second. I gotta. Python. What am I missing here? Decorator func wrapper, func wrapper. Why am I getting an error? Yeah.
Sorry, go ahead.
No, go ahead.
Just saying that
why are you getting an int has no? I don't understand that. Oh, I see what I'm doing wrong. Args. got it right first. Okay. So now it should work. Please work. Fine, it didn't work.
Right, we can look at it during the either social hour or in the after hours. We can go into a bit more detail. But yeah, I use decorator all the time, but I still don't know how it works. So
let's see if it's complaining. This is one of those things where even though I've written these several times, I will often have to look it back up because there's always one little detail. There we go. Okay, wraps is what was complaining. Okay, so as you can see, this decorator, it's supposed to take the first argument, multiply it by 10. Okay, so when I put food 1, I get 10, and I do food 2, I should get 20. So what is essentially happening is what I actually have here is not my original foo. What's happening here is I have a completely new function, and that new function is, so you saw in my example, I had kinetic energy equals validate quantities, function equals kinetic energy light. So the food that I see here, so okay, let me do it let me do it this way. If I did foo and I did foo light in this case, okay, this foo that I get back from validate quantities is not foo light, or even to make it even more relevant, if I do mult 10, okay, this foo that I have here is not foo light. It's a new function, and that new function basically you progress through the order. So that new function does this, and then does what was done in foo light. Or to bring it even closer, it's more like this. So this foo would be this one here. This foo is what I'm using here, but this foo is masquerading as that one. You actually have an additional layer that is executing this line of code. So this decorator, if you notice that I define a function within the decorator, this wrapper function, and the decorator returns that wrapper function. So in this case, my foo here is actually this wrapper. Okay.
That makes sense. Kind of.
Yeah. So and it doesn't matter if mult 10 then new cell. Yeah, it doesn't. No. Yeah. Or do they have to be the same cell? Same cell, same cell. If I'm doing, this is a function in and of itself. So mult 10 can be used any number of times you want on any number of functions. So I could do I can now do a at mult 10 define bar y.
Yeah, Eric, I see
Return
that. My question was more like if you press enter, say 20 times between mult at mult 10 and def foo, does it still get it? Like,
Yes, it does. It stays in memory.
Mm-hmm.
so does it mean that between mult 10 and def bar, you can have any spaces you want, not anything else?
No, I think you have to. That's a good question on syntax, Eric.
Are you
have to have it? Do you have to have?
Are you
them
talking like
next to each other?
this?
Yeah.
No, you can't have spaces. They have to be connected to each other.
So that's how it knows that it just connected to that.
Yeah,
That's correct.
it knows
I was
this
just
is-
bringing that up.
that is part of the what we call the sugar syntax.
Right, but in your Jupyter lab notebook that you were showing to us, there was a space between the decorator and the function.
No.
Yeah. Right. Okay, I got tricked by the parentheses.
Mm-hmm.
Sorry about that.
No, you're fine. You're fine.
No, it brings up a good point because that really does answer Ramiz's question, which is how does the compiler know that the function that follows
Mm-hmm.
is the function that's going to go into the decorator? Well, that's a good question.
Yeah. Right.
Yeah. So the really nice thing about it is, for example, with validate quantities, we have this operation that we want to do many, 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 many times. So instead of having to write the code many, 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 many times, we write it once as a decorator that can be complied to any number of functions we want to apply it to. And beyond that, you can write decorators for class methods. In fact, validate quantities is designed to work with class methods. You can write decorators to work on classes. So what I think Clem, was you that was asking about wraps. So the wraps function, the wraps decorator that you saw me trying to do that was causing me problems, I have to go back and look at why. This wraps like that, that's a special tool in Python that you use in decorators that, excuse me, that allows this wrapper. So like I was saying up here, the food that I'm using here is actually wrapper and not the original food that I defined. So this wraps helps wrapper masquerade as the original food.
But you don't need it.
Oh.
Does it run that way?
So what it does is it specifically manipulates a couple of the dunders attached to foo such that as a user, it looks like the original function.
Yeah, I mean, if you have error messages or things like that, you'd rather the error messages point to the function that's being wrapped and not necessarily the wrapper function.
Yeah, exactly.
So it'll pass things and make it look like the original function. The downside to that is debugging, because if the problem is somehow that your wrapped function isn't playing well with your, this is more a question than it is a statement. If your wrap function isn't playing nicely with your wrapper, how do you troubleshoot?
So okay, so a couple points. So remember how I said during the notebook demo, I say ignore this right now, this kinetic energy light, even though I was using kinetic energy. That's because validate quantities is returning a function, this kinetic energy, that is masquerading as kinetic energy light. So that's essentially what's going on here. Is this decorator is designed to be used primarily in this fashion. So the function you're using would be kinetic energy, and the function you're using would be named the same as the one that you're decorating, opposed to this kind of more functional approach where the function you're using is not the same name as the function you're decorating. I don't know if I made any of that better, but
yeah, that was clear.
Okay.
Thanks.
And Will, on your point about debugging, this is the structure that I generally use for debugging, because if you use it in this structure, your debugger would end up stepping through your decorator code as well.
So that's how you debug.
So in fact, if you look at our tests, the majority of our tests use this pattern when testing.
to bypass something or to ensure?
Because I
However-
can write more elaborate tests with this pattern than I can do with the sugar syntax.
Okay.
I think we should continue with the demo now.
Yeah, sorry, a little bit. You got an extra long break. All right, but I think good
My
discussion.
bad.
What was that?
I said my bad.
No, it's all good. Hopefully everyone is getting something out of it. All righty. So back to the demo. I only have a couple more lines and then we can get back to the normal schedule. So this is great that we have this kinetic energy, but we have to put in a mass argument, which is kind of annoying for plasma physicists because we don't work with DeLoreans, we work with particles. And so that's where Plasma Pi's particle class can come from. So one way that we can interact with kinetic energy here is by using the particle class. So if we want to say, get the kinetic energy of an iron atom, the easiest way to go about it, for a function that looks like the current kinetic energy would first be from Plasma Pi dot particles import the particle class particle. Okay, and so we'll define a particle. Par equals particle with a capital P, and we're going to define a particle that is iron. Okay, enter, and we can quickly get the mass by doing par dot mass. So you do that and we get the mass of an iron atom. So then we could, using the kinetic energy function as before, you can do kinetic energy, okay, close the brackets, mass equals par dot mass, and velocity. I'm going to use this same 88 miles an hour. I'm going to do velocity equals velocity. Okay, shift enter. Now I got the kinetic energy of a single iron atom moving at 88 miles an hour. Okay, so this is better than having to go and look up the mass of an iron and hard code it. So now if we want to quickly change it up to, I don't know, xenon, all you have to do is put xenon in and re-execute and you get what it would be for xenon. So that's really nice, but we can still do better with it. And that's where the particle input comes in. So we'll go from Plasma Pi dot particles, import particle. We want import particle input now. Okay. And using the same, so particle input is also a decorator. So we can now, define kinetic energy, we're going to redefine kinetic energy. So we define kinetic energy and we're going to start with velocity. And this is going to be u dot meters dot u dot sec over u dot seconds. And instead of using mass, we're going to use particle with a colon, and we're going to decorate this as a particle. Okay. Close parentheses, and this is still supposed to go to a u dot joule. Okay. And then we'll do the kinetic energy calculation. So return 0.5 times particle dot mass. Now, again, everything in Plasma Pi is SI. So you're guaranteed that particle dot mass is in kilograms. So you don't have to do any additional unit checking because we make sure everything in our package is SI. So everything will operate as expected. Times velocity squared. Okay, so now let's do our decoration. So the first decoration we want to do is at particle input. Okay, so this is functioning very similar to validate quantities. What it will be doing is it will notice that there's a particle decoration annotation here, and so whatever is passed in for particle, it will double check that that is a valid particle. It will throw any errors if it's not a valid particle. And if it is a valid particle, it will actually convert it into a particle instance like this up here. Okay. But we still have units to validate. So on top of this, we can still do validate quantities. We don't have to add any additional parameters here because unlike mass where we had to enforce that it can't be negative, we don't have to do that anymore. So now all you have to do is decorate with validate quantities, then particle input. Okay. So shift enter. So now you can do kinetic energy. Okay. And we'll use velocity equals velocity. So it's still that 88 miles an hour. And we'll do particle equals, since I use xenon above, I'll use xenon here. Xenon. Whoops, shift enter. And we'll get the energy of a xenon atom moving at 88 miles an hour. Okay. And if you wanted to move back to iron, all you have to do is come back, choose iron instead, shift enter, and you'll get the same calculation for iron. Okay. And if we don't do, let's say, if you use something not a particle, okay, then it's going to show an error. Okay. In kinetic energy, particle equals not a particle. It does not correspond to a valid particle. Okay. You can also do things like if I put a value of 4 in here, it should be for helium. So you can do the same thing for helium. All right. Any questions?
You might have answered this earlier, but if I don't want to do the calculations in SI, but I still want units, like say I want to do the calculations in EV, under the hood, can you still do it in EV, or are you forced to convert first to SI and do the calculations in SI?
No, if you're writing your own function and you want the stuff inside, sorry, if you're writing your own formulary function and you want to use electron volts inside that function you're decorating, all you have to do is when you come back to validate quantities, you just go, if this was temperature, you just go, this is u.ev. So let's do a quick example. So if I wanted to define a function temp in Kelvin, right? And I'm going to require an input argument of temperature, and I'm expecting this to be in EV. Okay. And I'm going to go return, and I'm expecting the output to be in Kelvin, in U dot Kelvin. Okay. T. Okay. This is a little sloppy, but and let's multiply this by just so we're doing something else, multiply it by 10. So I can do at validate quantities, and that will do it all for you. So now if I put in temp in Kelvin and I put in one EV, so you were expecting EVs instead of Kelvin, so I put 1 EV in and I do this. I see why. So the reason why this is complaining, as I mentioned before, EV to temperature is not a
Proper conversion.
It's not a proper conversion. So if you
Charge
want
voltage.
if you want to do it like this, you do validations on return equals equivalencies colon u dot not end quote colon u dot temperature energy. I believe I have to close that up. So now it should work. Okay, so now it's just complaining that I didn't pass EVs in, so it's assuming I meant EVs. Okay, so let's make sure that this is right. So I passed in 1, and it's supposed to multiply by 10, so I technically passed in 10 EV, U dot EV. Okay, and so let's convert this to Kelvin. U dot Kelvin equivalency equals U dot temperature energy, shift enter, and you see we get the same thing. So even though in Plasma Pi we enforce SI units with inside our functionality, and we enforce our return arguments to be in SI units, validate quantities doesn't care. So you can specify, so when you're using validate quantities, you can specify any kind of unit you want to use. Okay, so adding the particle decorator makes it so we don't have to worry about ensuring the particle input is of a particle class. Yeah, you don't have to worry about it being a particle class. It just has to be what we refer to as particle-like. It has to be something that's recognized to be a particle. So a string or an int. Nick can probably expand better than I can on what particle-like instances are.
Right. It'll be an atomic symbol, possibly dash mass number, and then like ionic information. Or if you give particle a number, that will be treated as the atomic number. So you can create a particle that way. And like for particle input also, if the thing is already a particle is also particle-like. So it'll work through fine.
Mm-hmm.
I'll put a link in the chat because I'm pretty sure.
Atomic number, or is it the Z?
So if you give particle only one number,
Like
it will
4.
be that will be beryllium.
Oh,
and then
okay, that
you have
wasn't
to-
helium. He said 4 and said helium before, and so
Wait, what?
the-
Oh,
previously Eric had said he put a particle value of 4 and called it helium, when in reality it was beryllium and had some extra neutrons going with it.
that could very well be if you had Z equals 4. That would be the charge number. So how many electrons have been lost? And if you put mass num equals, then that would give the mass number.
So when the way Eric did it, when he just said particle equal to 4, was that by default, does that correspond to the mass number or the atomic number?
That would be the atomic number.
Okay, then in that case, I misspoke. It was beryllium, not helium.
I see. Okay,
Yeah.
thanks.
Got it.
Coming from astronomy.
So the lack of specifying units specifies the number of protons in the nucleus.
Right.
Got it.
And then I was going to make a quick note in the Plasma Pi documentation. We do have a glossary. So if you go to the glossary, it will define a lot of these parameters. So we define what does particle-like mean. There's a description in here what particle-like means.
How rich is your database? Like, are all the isotopes accounted for?
Yep. The data, we probably should update the data from like 3 or 4 years ago, but we went to the NIST, National Institute of Standards and Technology database, and got all of the isotope masses and things like that from that. So we did a pretty thorough job.
Nick did a pretty thorough job.
Yep, it
Thanks,
was.
humility.
Well,
I have to put him up on the stage at times because he's never going to put himself up on the stage. He did a really good job with it.
It was mostly procrastination-driven development again. So Plasma Pi started
best.
as procrastination-driven development.
The best kind.
Oh yeah, and Eric, could you put a link to the particle-like stuff in the chat?
Sure. Yeah.
And if there are parts of the
Oops.
definition for particle-like or any parts of the documentation that are confusing or could be clarified, those are like great pull requests to make, or also issues to raise. Like we're always looking for ways to improve our documentation. Again, procrastination-driven development. So.
All right. I say we're really close to the lunch break. Sorry that notebook and walkthrough took a lot longer than I was originally anticipating, but hopefully it was useful for all of you. I figured that were you say something, Nick? No. I figure we go to break early. I'll stick around and answer any more questions that people have, and then Nick and the rest of the community, I figured that we go back into formulary stuff after the break, and we can continue working on the formulary items and including validate quantities and particles into the formulary functions that the participants are working on.
Sure, and if there are other projects that any of us want to work on, feel free to bring it up in the chat or on Discord or raise an issue in the Hack Week repo. And we can, like, this is, I think the rest of the Hack Week is going to be fairly free form. So there's a lot of opportunity for participant-driven activities, stuff, things. Hard to think of words.
All right, thank you, Nick, and thank you everyone else. I figured, okay, we can take a break and return in about an hour and 10 minutes. All right, see you all then.
Thanks.